Okay, so Vijay, over to you. Thank you.
Thank you, Antonella. Thank you, Ram, for all the work in organizing this conference. It's been really good. Hello, everybody. Welcome you all to the first session of the eEnergy 2021 conference. So this session is in the design and operation of distributed energy resources. My name is Vijay Arya. I work at IBM Research, and I'll be chairing this session. So to get on with the session, there are actually 4 fabulous papers, including 1 nominated for Best Paper Award in this session. So we have 3 full papers, I believe, and 1 notes paper. And as Antonella was mentioning, we're going to spend about 23 minutes for the presentation of full papers, 7-minute question and answers, and 15 minutes plus 5 minutes for notes papers. So what I'm going to do is, as a chair, to keep track of the time and so on, I'm going to sort of raise my hand 2 minutes before the allocated time, something like this. So I hope the authors can see my raised hand. So and then I'm going to lower my hand when your talk ends. And if you exceed 23 minutes, I'm going to sort of unmute myself and request you to wrap up in the next 30 seconds or so. So with that, let me introduce the first speaker. So the first speaker is actually Yanfang Mo, who's going to give a talk on optimal online algorithms for peak demand reduction maximization with energy storage. Yanfang Mo is a research associate at the City University of Hong Kong. She received her PhD degree at Hong Kong University of Science and Technology, and also was a visiting researcher at the University of California in Berkeley. Her research interests include online optimization, combinatorial optimization, research allocation, and their applications to smart grids and intelligent transportation. She also received Best Poster Paper Award at Infocom 2021, and also got a Hong Kong PhD fellowship. So over to you, Yanfang.
Yes, thanks for your kind introduction. And can you see my slide?
Yes.
Thanks. Hello, everyone. It's lucky for me to give the first talk of the first session. Hope you'll enjoy my talk today about the paper titled Optimal Online Algorithms for Peak Demand Reduction Maximization with Energy Storage. This is joint work with Qiulin, Minghua, and Zhou. My name is Yanfang Mo. We're all from the School of Data Science, City University of Hong Kong. Demand response is a promising paradigm for future power systems. It benefits both the supply side and the demand side. The core idea is to incentivize electricity users to adapt the power consumption behaviors in response to supply conditions. For example, users may shift the load from on-peak hours to off-peak hours to get a smoother load curve, which the supply side can easily track. Behind the demand response, this huge market is estimated that the global demand response capacity will grow to almost 200 gigawatts in 2023. For utilities, pricing is a very popular demand response mechanism. Utilities first introduce volume pricing for the amount of energy as a real-time price trajectory. As we can see, utilities use the time-based electricity price differences to motivate customers to shift the load according to short-term supply conditions. The electricity price can change as fast as every 5 minutes. In addition, utilities introduce peak demand pricing specifically for the maximum power during a billing period. The power is measured every 50 minutes. The purpose of peak demand pricing is to regulate load according to long-term supply planning. As we can see, both peak demand pricing and volume pricing are popular all over the world. There are some sample tariffs from PG&E in the United States, CLP in Hong Kong, and Shenzhen. Initially, the peak demand pricing rate and the volume pricing rate have different units. However, we know that the power is measured every 50 minutes. We can unify the two units and say that the peak demand pricing rate is much higher than the volume pricing rate. Thus, it's not surprising to say that peak demand charge dominates the BLs of large load users. There are some examples of large load users like data centers and EV charging stations. In the United States, for over 1/4 commercial customers, the peak demand charge accounts for 30 to 70% of the electricity bills. Particularly for EV charging stations, the portion of peak demand charging in a BL can be up to 90%. We also observe similar phenomena in other places of the world. As the increasingly popular demand response scenario under our consideration, we consider a large load user. The user uses renewable generation from solar panels or wind turbines, and an energy storage system based on fuel cells or batteries to reduce peak demand. Note that the fuel cells usually do not allow recharging in operation. The peak minimizing intervals of large load users benefits both the user and the grid. It can improve grid reliability and delay infrastructure upgrade, to bring win-win benefits. There are also other intervals on using local generation for peak optimization. We have focused on this popular demand response scenario. The large load users use renewable and energy storage to reduce peak demand. However, it's rather challenging to realize the win-win benefits in practice because the net demand is highly uncertain. The net demand refers to the difference between the gross demand and the behind-the-meter renewable generation. As we can say, the individual node is highly fluctuating, and the small-scale renewable generation of the large load user is highly volatile. As a result, the difference, the net demand, is harder to predict. We are challenged by the peak optimization and the uncertainty with inventory constraints. It's well known that this is a challenging problem and largely open. Before our work, there are some results about energy storage management and peak optimization. Some researchers use uninterrupted power supply or vehicle-to-grid services to reduce volume charge, operation cost, greenhouse gas emission. Some researchers focus on peak optimization by the routing techniques, predict and optimize the first estimate the statistics or exact values of future information, and then use stochastic optimization or model predictive control to do energy storage scheduling. Some papers even assume that they know the amount of peak demand. These are very nice results. However, they are either inapplicable to peak optimization or rely on predictions. This motivates our work. In this slide, we'll show the contributions of our work. First, we focus on maximizing peak demand reduction with energy storage under the online circuit, where the net demands are revealed sequentially in time, and we have to make decisions irrevocably. We design an optimal online algorithm with respect to the competitive ratio. It means that there's no other deterministic or randomized online algorithm which can attain a smaller competitive ratio than our algorithm. The smallest possible competitive ratio is the best possible competitive ratio. It's also called the price of uncertainty, the value of prediction, because it indicates how much improvement we can obtain if we know perfect prediction of future information. We show that we can characterize the price of uncertainty in polynomial time. Furthermore, we design an adaptive online algorithm with optimal worst case performance and strong average case performance. Usually, online algorithms are criticized for the focus on worst case analysis. However, worst cases may rarely happen in practice, and most online algorithms are not adaptive to the input in the runtime. How our adaptive algorithm addresses these common criticisms for online algorithms. Moreover, we show that our adaptive algorithm achieves 20% more peak demand reduction than popular alternatives in simulations based on real-world traces. Later, I will introduce the details of our work. If you have any questions, please feel free to interrupt me. As the problem formulation, we consider an on-peak period of T sequential time slots. The input of this problem are the net demands over the T sequential time slots. We assume that each unknown future net demand is within a given interval. Here we assume a uniform net demand lower bound and net demand upper bound. Our results and algorithms are also applicable to the case where each time slot have different lower bounds and upper bounds. Our objective is to maximize the peak demand reduction. The peak demand reduction is the difference between the peak net demand and the peak procurement from the grid after using the energy storage. That means the peak demand reduction directly captures the benefits of using energy storage. In this problem, we only consider discharging of the energy storage because we consider general storage system, fuel cells, and flywheels do not allow charging in operation. We also have a follow-up work which consider both charging and discharging in operation. So since we only consider discharging here, the discharging decisions should obey the storage constraints. The total amount of discharging energy storage should respect the storage capacity, and the discharging amount at each time slot should not exceed the discharging rate limit. This problem is easy to solve if we know all the net demands. The question is, we are interested in the more practical setting. This is challenge setting because the demands are sequentially revealed and the decisions should be made irrevocably. The discharging decisions are coupled in time due to the capacity constraints because the total amount of discharged energy storage should not exceed the storage capacity. And it's well known that the peak optimization under uncertainty is particularly difficult because one bad decision in this problem may be fatal. Future decisions may not even compensate a little for the loss of this bad decision. Our focus is to design effective online algorithms for this challenging peak optimization under inventory constraints problem. We shall use competitive ratio to evaluate the performance of an online algorithm. The competitive ratio of an online algorithm is defined as the largest possible ratio between the peak demand reduction under the optimal offline solution where we have perfect future information and the peak demand reduction under the online algorithm where we do not assume any future prediction over all possible inputs. From the definition, we say that the competitive ratio measures the worst case performance of the online algorithm. Usually the competitive ratio is no smaller than 1. And we prefer online algorithms with a smaller competitive ratio. If the competitive ratio is 1.25, it means that for any net demand, our online algorithm without prediction can achieve at least 80% of the optimal offline peak demand reduction under the optimal offline case where we have perfect information. Competitive ratio and online algorithms also find the applications in other energy system problems. Here we list some papers for your future reference. Now let's go back to our own algorithm. We design a class of algorithms. Each algorithm is parameterized by a given ratio. The idea is quite simple, just to keep the offline to online competitiveness to be at most the given ratio. Specifically, at each time slot, we determine the discharge amount of energy storage, such that this offline to online ratio is no more than the given ratio. The denominator refers to the online performance and the nominator refers to the critical offline performance, given the observed inputs and the implemented actions so far. In this way, if for all possible net demands, the discharge rate limit is respected and no storage underflow happens, then the given ratio is exactly the competitive ratio of the designed online algorithm. That's good news, but the question is, how do we know if the given ratio is achievable or not? If for all possible net demands, the resulting discharging amount at each time slot always respects the discharging rate limit, and the total amount of discharged energy storage does not exceed the storage capacity. If we are aggressive, we give a smaller ratio. For example, we set the ratio to be 1. We expect that the online performance is exactly the same with the offline performance. That's the ideal case, but that's impossible because of the existence of uncertainty. If we give a very large ratio, the resulting discharging solutions are always feasible. However, the resulting competitiveness is not preferred because the competitive ratio of the resulting algorithm is pi, and pi is very large. We expect to find the smallest achievable ratio among the designed class of algorithms. Likely, we show that given the storage parameters and the net demand bound and the number of time slots, we can obtain the smallest achievable ratio among the designed algorithms by solving at most t linear fractional problems. We all know that the linear fractional programming is not much harder than linear programming, thus we can obtain the smallest achievable ratio in polynomial time. In practice, one can compute the smallest achievable ratio beforehand and then run the best algorithm. Most surprisingly, we find out that this smallest achievable ratio is the best possible competitive ratio among all deterministic and randomized online algorithms for the considered problem. The best possible competitive ratio is also called the price of uncertainty because it indicates how much improvement we can obtain if we can have perfect prediction of future information. Combining the two results, we show that we can characterize the price of uncertainty in polynomial time. Following are some numerical illustrations about the best possible competitive ratio. We say that as we increase the storage capacity, the best competitive ratio decreases. Actually, when the storage capacity is extremely large, the best possible competitive ratio will approach 1. This means that if we have enough storage sources, we can expect that the performance on the offline setting where we have perfect future information and the online setting where we have no prediction, the performance under the two settings are the same. Moreover, we increase the uncertainty of the all possible net demands, and we say that the best possible competitive ratio increases as the uncertainty of net demand increases. This somewhat explains why we call the best competitive ratio the price of uncertainty. We have designed an intuitive algorithm with the optimal competitive ratio among all deterministic and randomized online algorithms for this peak optimization on the inventory constraints. And we also show that the best possible competitive ratio can be computed by solving a linear number of linear fractional problems. In most cases, online algorithms are criticized for the focus on the worst cases, while worst cases may rarely happen in practice. And most online algorithms are not adaptive to the particular net demands in the runtime. Can we retain the best worst case performance and improve the average case performance? The answer is yes. If we observe none of the future net demands, we can only pursue the best possible competitive ratio we compute beforehand. However, as time goes on, we observe more data, we should pursue a better ratio, a smaller ratio. This is called the best competitive ratio with respect to residual uncertainty. Similarly to before, the best competitive ratio with respect to residual uncertainty can also be computed by solving linear fractional problems. From this figure, we can see as time goes on, the uncertainty decreases and the best competitive ratio with respect to the residual uncertainty also decreases. This decreases indicates the strong average average case performance. Specifically, we design an anytime optimal algorithm. At each time slot, we determine the discharge amount of energy storage by keeping this offline to online ratio to be no more than the best competitive ratio with respect to the residual uncertainty. In this way, we can retain the same optimal worst case performance and achieve improved average case performance. Following, I will give some numerical results to show the strong empirical performance of our algorithms. We obtain real-world traces from an EV charging station in Shenzhen based on 3 months data. We identify the on-peak peak rate of day and the length demand bounds. There are 3 EV charging node curves, as we can see how volatile the EV charging node is. We compare our algorithm with some popular alternatives. Some are based on heuristics called threshold-based algorithms. Some are based on the classic receding horizon control. We show that our adaptive algorithm, which pursues the best competitiveness with respect to the residual uncertainty. This adaptive algorithm realizes a significant portion of the benefits of the storage. Even our algorithm do not have a prediction. Actually, this adaptive algorithm achieves 59% to 81% of the peak demand reduction under the optimal offline solution, where we have perfect future information. This result will serve as a benchmark for other future strategies when we could have some predictions. We also show that our adaptive algorithm realizes 23% more benefits of storage than threshold-based algorithms. This suggests that we should design more intelligent algorithms instead of simply relying on heuristics. Moreover, we show that our adaptive algorithm without prediction realizes 20% more benefits of storage than receding horizon control algorithms, which have a look-ahead window. This figure also indicates sometimes noisy prediction can generate very bad outcomes because this receding horizon control algorithm achieves very little peak demand reduction. That's not desirable. In this work, we first designed the fast and the optimal algorithms for the online peak demand reduction maximization under inventory constraints. We achieve the best competitive ratio among all deterministic or randomized online algorithms for this problem. We also show that we can characterize the best competitive ratio, also called the fundamental price of uncertainty, in polynomial time. We also design an anytime optimal algorithm with the best worst case performance and strong average case performance by adaptively pursuing the best competitive ratio with respect to the residual uncertainty. Furthermore, we show that our adaptive algorithm can achieve 20% more peak demand reduction than popular alternatives in simulations based on real-world traces. These are some interesting future work directions. Specifically, we already have some interesting results in the more complicated case where we now both charging and discharging in operation. And our objective is to minimize the sum of volume and peak demand charges instead of the peak demand charge only. That's my presentation today. If you have any questions, please feel free to ask me and send us emails. Thank you.
Thank you, Yanfang, and perfectly on time and much ahead of time. So thanks a lot for the excellent presentation. I think we have one question from Professor Srinivasan Keshav. So Keshav, can you unmute yourself and ask your question?
Yes, thanks, Vijay. Thank you for this talk. I'm sorry, I have a really naive question, which is in the optimization objective, you're saying its objective is max D minus max D minus delta. So if you could just show the slide with the problem formulation.
Yes, I see. We have a backup slide about this question. Our focus is to maximize the peak demand reduction.
No, I'm sorry. I'm just looking at the optimization objective of the problem, which was the which you had in the earlier slide. It's
yes. So wait one moment.
Yeah, so if you just look at the slide over here, so the optimization say you said basically doing max D minus max D minus delta. So D minus delta is the is what you're going to get after you include storage, right? So that's what you're getting from the grid. And why do you have an extra term of max D minus delta? I mean, I'm just trying to understand the objective function. If you could explain that, please.
Yeah. Yes. Let me try to answer your question. Thank you for your kind question. If we do not use energy storage, this part, the peak demand, this part is what we need to pay for peak demand pricing. And if we use energy storage, this part is the what we need to pay for the peak demand pricing.
Right.
However, if we know all the net demand, maximize the difference of the two peaks or minimize the peak procurement from the grid are exactly consistent because we know the peak net demand is just a constant, right? The question is, we consider online setting. In the online setting, we do not know the value of peak net demand.
Right.
So, in my opinion, from this point of view, it's much more difficult to maximize the difference of the two peaks in our online setting. Moreover, we think that the peak demand reduction directly reflects the benefits brought by using energy storage, right? This will help us identify the optimal sizing of the storage capacity.
I see.
Yeah, hope I have answered your question.
Okay, yeah, I'll have to think some more about it, but thank you. Yeah, I can see that in the online setting, this particular formulation is certainly a different one. It's not an intuitive one anyway, at least to me. But I'll think some more about it. But thank you for your answer.
Thank you. Actually, I want to add one more point because we use competitive ratio to evaluate the performance of online algorithms. Actually, on the competitiveness, under the performance measure of competitive ratio, they have different definitions on the minimization problem or maximization problem. So when we use competitive ratio, the two problems are totally different.
Okay, thank you.
Yeah, thanks.
Okay, I think there's another question. Is it Jay? Jay, do you want to ask a question?
Yes, thanks. So Yanfang, my question is the following. So currently you have this methodology of computing the competitive ratio looking forward, right? Based on what has been seen, you want to compute what is the worst case competitive ratio that you can expect. My question is, if you have additional information on how, for example, the demand can vary, so that goes slightly away from the worst case setting. So for example, if I told you that the demand would not change by much in one time unit, right? For example, the demand can only change somewhat slowly. Would that kind of additional information would it be possible to bake that kind of additional information to compute potentially a better competitive ratio under your methodology as well?
I think the rough answer is yes, because we are computing the best competitive ratio. The best possible competitive ratio is also called the fundamental price of uncertainty. So in your description, the uncertainty should decrease because we have more information. In this case, in this model, the best possible competitive ratio should become smaller, which means better. I think in this case, our algorithmic framework will still work, but we need to find another way to compute the smallest achievable ratio.
Great. Yeah. Thank you.
Thank you.
Okay, we may have time for maybe another quick question. Any other questions?
May I ask a question?
Yes,
yes.
please go ahead.
Thanks for the presentation. So I have a question about from the big picture, actually. So may you comment about compared with the regret-based online algorithm design with this computer ratio-based online algorithm design? So as we know, so in the machine learning society, so currently the online convex optimization algorithm or online control algorithm, they always use this regret to design the algorithm. But what's the difference between this computer ratio and regret? Or is there any advantage compared with this regret when using the computer ratio? Thanks.
Thank you for your question. At this moment, I can show you some my understandings about the difference between regret and the competitive ratio. However, I think it's difficult to say which one is better because I think regret and competitive ratio are both good algorithm performance measures, and they have their own benefits and weaknesses. For competitive ratio, as you say from this formula, it's defined as the ratio between two performance on the offline setting and the online setting. However, for regret, it's the difference of it's the maximum difference between the performance of the two settings. That's the difference of the two performance measures in definition. However, whether you need to choose competitive ratio or regret in your application, I think it depends on your application. In our problem, we think that the competitive ratio is a better performance measure.
Okay, I see. Thanks a lot.
Thank you.
Right. Can I add one more comment?
Okay.
I think in addition to the relative difference and absolute difference, I think if you refer to OCO, online convex optimization, usually the regret there is respect to the best dynamic offline solution. While for the competitive ratio analysis, we usually refer to the dynamic version of their offline solution. The difference is that for static offline solution, the solution cannot change across time slot. Okay, so it has to, if you decide to discharge, let's say for this problem, 5 kilowatts per hour, then you have to keep doing so. So we think that static benchmark, static offline decision as benchmark may not be very interesting for our setting. Okay, and further, OCO usually is for the setting where you first make your decision, and then the cost or the price get reviewed. But which is different from our setting considered here, which you may have already have some information about the net demand for the next 15 minutes. And so because of these two reasons, we focus on the competitive ratio analysis instead of the regret analysis. I hope this answered your question to a certain extent.
Yeah. Thanks a lot. So as you mentioned
Jiang, sorry, we kind of run out of time.
Sorry.
Is it okay? Is it okay to continue the discussions in Slack, please?
Yeah. Okay. Thank you.
Yeah, thanks. Yeah, Hartmut, Shwek, sorry, I missed your question. So I also request you to please put your question on Slack in the session 1. There you can put your question and request the authors to kindly take a look at Hartmut's question as well. So thank you, Yanfang, for the really good presentation and the subsequent discussion. So let's move on to the